I'm going to go ahead and post the formatting for the triangles shown in 5-5. And today you were introduced to two new ratios. The sine ratio, which is a comparison by division of one of the legs to the hypotenuse. The sine ratio compares the length of the leg opposite theta to the length of the hypotenuse of the triangle. So you will see the sine ratio written this way. We're not using change in y and change in x as often any longer because the triangles aren't oriented in standard position all the time. The cosine ratio compares the length of the leg adjacent to theta. In other words, it's one of the rays that creates that angle. And it has a distance from vertex A to vertex C in this triangle called ABC. And we often see cosine theta written this way, adjacent over hypotenuse. And if I were practicing with these ratios for the first time, I would write cosine theta equals adjacent over hypotenuse every time I started a cosine problem, and I would write sine theta equals opposite over hypotenuse every time I started a sine problem. So together, I'd like you to write what I write. Let's look at the examples in 5-5. A starts with copying the triangle. 17 degrees is theta. And you're just copying this right outside the book. Now, I'm seeing that I have a value for the adjacent leg, and I have the hypotenuse. So I want to choose the ratio that lets me use direct substitution of the length of the adjacent leg in comparison to the hypotenuse. So which guy is that? For this example, I would like to use cosine, and my angle of reference is 17. My substitution then will be cosine of 17, adjacent value is 3, hypotenuse value is x. Now, I don't love it when x is in the denominator, but I know that if I multiply both sides by that denominator, I will reduce the denominator on the right to a value of 1 because x over x is 1. So I'm left with x cosine of 17 equals 3. And I really want to isolate my x here, so I'm going to divide both sides by cosine of 17. And I really don't need to push any buttons in my calculator until I get to the very last step, where x is exactly equal to 3 divided by cosine of 17, and it's approximately equal to, grab your calculator and push those buttons, making sure you're in degree mode. 3 divided by the cosine of 17 is approximately 3.14. So these are all required steps. Draw the triangle, choose a trig function. That would be tangent, sine, or cosine, based on the information you have in your triangle. Set up an equation, bust the fraction. These are all ratio problems. And show the solution in both an exact form and an approximate form. So let's go through all 5 steps for the triangle in B. Step 1, draw that triangle. The triangle shown has a hypotenuse of 9. My reference angle in this case is up here at 25, and I can tell that I have the side opposite 25. And my opposite side was highlighted with green in my original triangle. So I want to choose the ratio that has the opposite compared to the hypotenuse. So I'm going to choose the sine ratio. And each time I practice one of these problems, I'm going to rewrite the ratio because I really need to reinforce my memory of which ratio compares which sides. My substitution shows the sine of 25 is the opposite, which has a value of x in this case, to the hypotenuse, which has a value of 9 in this case. I bust the denominator of this ratio, and 9 sine 25 is a calculation that my calculator can handle. So I have a side length that's approximately 3.80. So each of these steps is important. In C, we draw the triangle. Oh, this is one of my favorites. I love to see the 45, 45, 90. Because x has to equal 5, I know I'm looking at a tangent ratio that is 1 to 1. Now, yes, I know that x is 45, but let's justify that. Tangent 45 equals, and remember the tangent ratio? Tangent theta is opposite over adjacent. So tangent of 45 is x over 5. 5 times the tangent of 45 is exactly equal to x, which is exactly equal to 5 because this value right here, tangent of 45, We know that's a 1-to-1 ratio, so it equals 1. But push those buttons anyway, just to make sure your calculator's in the correct mode. D, we draw the triangle first. X, 5, 62 degrees. Now you've got some choices for each of these, right? 90 minus 60 gives you the complement. 90 minus 62 gives you the complement of this angle. You know this is a 28-degree angle. So if you want to use cosine, you can. If you want to use tangent of 28, you can. If you want to use tangent of 62, you can. Either of those is a legal use here. So tangent of 28 is x over 5. I kind of prefer that to tangent of 62, which is 5 over x. We're going to get the same value for each calculation, but there's one fewer step in this tangent of 28 calculation, because I go directly to x equals 5 tangent of 28. When I put that in my calculator, I have a value of approximately 2.66. Now, if you like the extra steps, we can reduce x over x to a value of 1, but now I've got to divide both sides by tangent of 62. X times the tangent of 62 is equal to 5. Divide both sides by tan 62 in order to isolate x. X is approximately 5 divided by tangent 62. I'd better get 2.66, and I do. Still approximately 2.66. So you've got some flexibility here. You should be trying to practice both ways. This is your time to practice so that you see what's happening. So keep watching while we do E together. Now E is formatted in a way that is not really comfortable for me to look at it, but I'm going to work really hard to visualize what I have here. I see the hypotenuse, and I see the leg opposite 34, which is my reference angle in this case. So opposite over hypotenuse matches my definition for the sine of theta. So I'm going to apply sine 34 equals 13 over x. Multiplying both sides by x. X multiplied by the sine of 34, which is just the ratio of the opposite leg to the hypotenuse, equals 13. I need to divide both sides by 34. Each of these steps needs to be documented in your work. X equals 13 divided by sine of 34, because sine 34 over sine 34 equals 1. And x is approximately 23.25, 23 1/4. Now what if you liked the complement of 34 just a little bit better? What if you liked 56 better and you liked working with cosine better? Now I have the angle that's adjacent